Every second you have been sitting here, the observable universe got a little smaller. Not because galaxies are dying, because space itself is stretching faster than light can cross it, and 20,000 galaxies just slipped past the point of no return. We're not running out of time to leave the solar system, we already ran out. Voyager 1 has been falling away from Earth for 48 years. It is the fastest object humanity has ever built, and at its current speed, it would take 73,000 years to reach the nearest star. A star, by the way, it is not even aimed at. We celebrated that spacecraft like a beginning. It might actually be proof of an ending. Tonight I want to walk you through the real math, the real physics, and the real reason why we might never leave the solar system. Stay with me. If you're new here, subscribe and get comfortable. Because tonight I'm going to take apart every escape plan humanity has ever dreamed up. The nuclear engines, the laser sails, the generation ships, the antimatter drives, and show you the exact point where each one breaks. And then I am going to show you something worse. Why fixing one problem always makes the next one harder. Now, settle in and let's ease into it. Part 1. The Voyager Illusion. On September 5th, 1977, a small aluminum spacecraft no bigger than a compact car was flung off the surface of the Earth on top of a Titan IIIe Centaur rocket. It carried a golden record etched with greetings in 55 languages, the sound of a human heartbeat, the brain waves of a young woman in love, and a map, a pulsar map, designed to tell anyone who found it exactly where in the Milky Way this object had come from. That spacecraft was Voyager 1. And at the time of its launch, no one imagined it would still be travelling nearly half a century later. As of 2026, Voyager 1 has been falling outward from Earth for more than 48 years. It has crossed the orbits of Jupiter and Saturn, surfed through the heliosheath, and in August of 2012, it became the first human-made object to officially enter interstellar space, or at least that is how the headlines described it. It is moving at roughly 17 kilometers per second relative to the Sun. That is about 38,000 miles per hour. That is faster than any bullet ever fired from any weapon on Earth. It is faster than anything humanity has ever deliberately sent outward into the galaxy. Voyager 1 is our speed record, and it has held that record for decades. So let me ask you something that should bother you more than it probably does. If this is our fastest object, our crowning achievement in outward velocity, how long would it take Voyager 1 to reach the nearest star? The answer is approximately 73,000 years. And the star it would theoretically reach, Proxima Centauri, sitting about 4.24 light-years away, is not even a star Voyager 1 is aimed at. It was never pointed there. Its trajectory was shaped entirely by the gravitational assists it borrowed from Jupiter and Saturn in the late 1970s. And after those flybys, Voyager entered a long, unguided ballistic drift. It is not heading toward any star system in particular. It is heading toward a whole lot of nothing for a very, very long time. Now think about what that number actually means. 73,000 years. Homo sapiens have existed in anatomically modern form for roughly 300,000 years. The oldest known cave paintings are about 40,000 years old. Written language is around 5,000 years old. The entirety of recorded human civilization, every empire, every war, every discovery, every poem, fits inside a window of time that is less than 1/10 of the travel time Voyager would need to reach the nearest star. And remember, this is the nearest star. Most stars in our galaxy are hundreds or thousands of light-years away. At Voyager speeds, those distances do not just become impractical. They become geological. They become evolutionary. They stop being travel times and start being extinction timescales. There was a moment in the late 1970s when humanity looked at Voyager and felt something close to triumph. The golden record was the product of a committee led by Carl Sagan, and it was assembled with the sincere hope that someday, perhaps millions of years in the future, an alien intelligence might intercept this small craft and learn that life had existed around a yellow dwarf star in the outer arm of the Milky Way. That optimism was beautiful. It was also, in hindsight, quietly tragic, because it assumed that flinging an object outward at 17 kilometers per second was the beginning of an interstellar journey, when in reality it was the end of one that never really started. Here is the part most people miss entirely. Voyager 1 has not actually left the solar system. Not in any physically meaningful sense. The heliosphere, the bubble of charged particles blown outward by the solar wind, ends at roughly 120 astronomical units from the Sun. Voyager crossed that boundary, yes, but the solar system does not end at the heliosphere. The Sun's gravitational influence extends thousands of times farther than that. The Oort cloud, a theoretical shell of icy bodies loosely bound to the Sun, stretches from about 2,000 astronomical units out to perhaps 100,000 astronomical units. Voyager 1, after nearly 5 decades of travel, is currently around 165 astronomical units from the Sun. It does not even scratch the inner edge of the Oort cloud. At its present speed, it will take Voyager roughly 30,000 years just to cross through the Oort cloud, not to reach another star, just to leave the Sun's gravitational neighbourhood. So when someone says Voyager 1 has entered interstellar space, what they really mean is that it has exited the solar wind. That is not the same thing. It is not even close. The solar system, defined by gravitational influence, is so unimaginably larger than the region we associate with it, the planets, the asteroid belt, the Kuiper belt, that Voyager has, in effect, walked from the front door of a house to the end of the driveway and declared itself in a different city. And this is the fastest thing we have ever built. That fact alone should reshape how you think about every headline you've ever read about interstellar travel, every proposal, every artist's rendering, every TED talk about the stars. Because if Voyager 1 is our benchmark, and it is, then we have not demonstrated the ability to travel between stars. We have demonstrated the ability to crawl within our own gravitational basin at speeds that would make interstellar arrival a mathematical abstraction, a number so large it stops being a plan and starts being a prayer. The real question is not whether Voyager will reach another star. It will not in any way that matters to anyone alive today, or anyone alive in 1,000 years. The real question is what Voyager's speed tells us about the gap between where we are and where we would need to be. And the answer to that question is what this entire story is about. Because if our fastest piece of technology is still geologically slow, then the problem is not effort. The problem is not ambition. The problem is something built into the structure of the universe itself, a set of overlapping constraints that do not care how clever we are or how long we wait. And the first of those constraints is one most people have never even thought about clearly. It is the size of the cage we're sitting in. Part 2. The solar system is not a neighbourhood. Most of us carry around a mental picture of the solar system that was handed to us in elementary school. You probably remember it, a neat row of planets spaced out along a line, starting with Mercury close to the Sun and ending with Pluto way out on the edge, like houses on a suburban street. Some of those diagrams even had a little dotted line around the outside with a label that said Edge of the Solar System, as if there were a fence you could walk up to and peer over. That picture is wrong. It is not a little wrong. It is catastrophically wrong, and the way it is wrong matters enormously for understanding why interstellar travel may not be a problem that engineering can solve. The solar system is not a neighbourhood of planets with a clear boundary. It is a gravitational structure, and like all gravitational structures, it does not have an edge. It has a gradient. The Sun's gravitational pull weakens with distance but never actually hits zero. What we casually call the solar system is really several nested layers, each one dramatically larger than the last, and the one most people think of, the planets, is only the innermost sliver. Let me walk you through the actual structure, because the numbers matter. The innermost region, the planetary zone, extends out to Neptune at roughly 30 astronomical units from the Sun. 1 astronomical unit is the distance from Earth to the Sun, about 93 million miles. So the planetary zone is about 2.8 billion miles across. That sounds enormous, and it is, by human standards. But then comes the Kuiper Belt, a ring of icy debris stretching from about 30 to 50 astronomical units. Pluto lives here. New Horizons flew through here. And beyond the Kuiper Belt, things get truly unsettling. The scattered disk extends from about 50 astronomical units out to several hundred, filled with objects on wild, eccentric orbits kicked outward by Neptune's gravity over billions of years. And beyond even that, there is the Oort cloud. The Oort cloud is believed to begin at around 2,000 astronomical units and extend outward to somewhere between 50,000 and 100,000 astronomical units. To put that in perspective, 1 light-year is about 63,000 astronomical units. The outer edge of the Oort cloud may sit nearly 2 light-years from the Sun. Proxima Centauri, the nearest star, is about 4.24 light-years away. That means the Sun's gravitational sphere of influence extends roughly halfway to the nearest star. You're not living on the surface of a planet at the edge of a small stellar system. You're living at the bottom of a gravitational well that is approximately 2 light-years in radius, and every single object in that well, every comet, every asteroid, every dwarf planet, every grain of dust, is gravitationally bound to the Sun. Leaving this system does not mean passing a line. It means climbing a gradient that gets shallower but never flat, spending energy every step of the way, and doing it across distances that make the trip to Neptune look like stepping off a curb. Think about what escape velocity actually means in this context. To leave the surface of Earth, you need to reach about 11.2 kilometers per second. That is the speed at which Earth's gravity can no longer pull you back. To escape the Sun's gravity from Earth's orbital distance, you need roughly 42 kilometers per second. Voyager 1 achieved only about 17, which means it is technically still gravitationally bound to the Sun. It is just on an orbit so elongated that it will never come back within the planetary region. But never coming back to the planets and leaving the solar system are 2 very different things. And here is where this connects directly to why we may never leave. The problem is not that space is large. Everyone already knows that in the abstract. The problem is that the structure of our own stellar system is designed, by the laws of gravity, to hold things in. The Sun is not a campfire you can walk away from. It is a well. And the walls of that well are not vertical. They slope so gently that you can travel for tens of thousands of years and still not have climbed out. This is why Voyager, after nearly half a century, is still inside the system by any gravitational definition. It has been climbing the wall the entire time, and the wall just keeps going. Historically, our understanding of where the solar system ends has shifted repeatedly, and always in the same direction, outward. In the 19th century, the edge was wherever the outermost known planet was. When Pluto was discovered in 1930, the edge moved to Pluto. When the Kuiper Belt was confirmed in the 1990s, the edge moved again. When the concept of the Oort cloud gained scientific acceptance, the edge moved yet again by orders of magnitude. Every time we thought we had found the fence, it turned out we were still looking at the yard. The fence was always farther away. And the uncomfortable truth is that there may not be a fence at all, only a slow asymptotic fading of the Sun's grip, blending imperceptibly into the gravitational influence of the nearest stars. We are not on a surface. We are inside a field, and the field does not end. It just weakens slowly, across distances that our fastest machines cannot cross in any human-relevant time frame. This is the first layer of the trap, and it is far from the last. Because even if you could somehow escape the gravity well, you would immediately face something even more disorienting. The fact that being able to see the universe is not the same thing as being able to reach it. Part 3. The first broken assumption. There is a peculiar cruelty built into the way the universe presents itself to intelligent observers. You can see almost everything, you can reach almost nothing. Right now, our telescopes can detect galaxies that emitted their light over 13 billion years ago. The James Webb Space Telescope, launched in December of 2021, has returned images of galaxies forming just a few 100 million years after the Big Bang. We can map the cosmic microwave background radiation, the afterglow of the universe's birth, with extraordinary precision. We can observe supernova remnants, measure the composition of exoplanet atmospheres through spectroscopy, and catalogue billions of stars across the Milky Way. In terms of information, we are extraordinarily connected to the cosmos. We know more about the structure of distant galaxy clusters than we do about certain regions of our own ocean floor. But here is the trap. Every single piece of that information arrived by the same method: electromagnetic radiation, travelling at the speed of light. Photons are free. They cost nothing to send, nothing to receive. They travel at the maximum speed the universe permits, and they do it without fuel, without shielding, without life support, without decay. Light crosses the 4.24 light years to Proxima Centauri in 4 years and 3 months. It is the universe's perfect messenger. And the problem is that we are not made of light. Matter behaves nothing like radiation. Matter has mass, and mass requires energy to accelerate. Matter is subject to inertia, which means that every increase in speed demands an exponentially larger expenditure of fuel. Matter can be damaged by the interstellar medium. Matter ages. Matter breaks down. Matter carries with it the entire burden of physical existence that photons simply do not have. When you look up at the night sky and see the Andromeda galaxy, you are receiving photons that left that galaxy 2.5 million years ago, and they arrived perfectly intact, carrying with them detailed information about the stars and gas clouds they departed from. If you wanted to send a grain of sand to Andromeda at the same speed, you would need more energy than human civilization has produced in its entire history. The grain of sand would also take 2.5 million years to arrive, and it would arrive alone, with no way to report back. This is what I call the cosmic transparency bias. The universe is transparent to light in a way that makes it appear accessible, navigable, almost inviting. You look at the Hubble Deep Field image and see thousands of galaxies packed into a patch of sky, no bigger than a grain of rice held at arm's length, and the instinct is to think, it is all right there, but it is not right there. It is right there for photons, for matter, for you, for a spacecraft, for anything that weighs more than nothing. Those galaxies are not just far away, they are unreachable. They exist behind a wall that is not made of distance alone but of physics. The wall is the speed of light, the rocket equation, the energy density of available fuels, and the thermodynamic cost of keeping complex systems alive during transit. This asymmetry between observation and traversal is not a temporary engineering problem. It is a structural feature of the universe. Light can go everywhere because it has no mass. You cannot go everywhere because you do. And no amount of technological progress changes the fundamental relationship between mass, energy, and velocity. You can improve your engines, lighten your spacecraft, find more efficient fuels, and all of those things help. But they help logarithmically, not exponentially. The gap between seeing and reaching does not close. It narrows slightly, and then it flattens, because the physics that governs motion is not the same physics that governs observation, and there is no bridge between the two. The James Webb Space Telescope is a perfect example of this paradox in action. It can detect the infrared signatures of exoplanet atmospheres orbiting stars dozens of light years away. It can tell us, with reasonable confidence, whether a planet has water vapor, carbon dioxide, methane, chemicals associated with life. Within the next decade, we may have a catalogue of nearby worlds that show strong biosignatures. We may know, or strongly suspect, that life exists on a planet orbiting a star we can see in our night sky, and we will not be able to get there. Not in a year, not in a century, not in 1,000 years, at least not with anything resembling our current or projected technology. We will know life is out there and be unable to visit it. The universe will have shown us exactly what we cannot have. This is the cosmic joke, if you want to call it that. The universe is not hiding from us. It is showing us everything while keeping everything out of reach. Knowledge expands at the speed of light. Mobility does not. And the gap between those two rates is not shrinking, it is growing. Because every year we build better telescopes and discover more worlds we cannot visit, more galaxies we cannot approach, more structure we cannot touch. The observable universe gets richer. The reachable universe stays the same size, or as we will see later, actually gets smaller. So before we even talk about rocket engines and fuel ratios and the biological limits of the human body, we need to sit with this foundational realization. The fact that you can see the stars does not mean you can reach them. The fact that the universe is transparent to information does not make it traversable by matter. And if you have built your hopes for interstellar travel on the intuition that the cosmos is close because it is visible, then you have built on an illusion that the universe itself creates, effortlessly, just by letting its photons fly free while keeping its distances locked behind the laws of physics. The solar system is not a starting point. It may be an envelope. And the next question, the real question, is whether the distance to the stars is even the main obstacle, or whether something far more fundamental is standing in the way. Part 4. The scale collapse. Let me try to make you feel something that numbers alone cannot convey. Proxima Centauri is 4.24 light-years from Earth. That is roughly 40 trillion kilometers. If you drove a car at highway speed, say 100 kilometers per hour, without stopping, it would take you about 45 million years to get there. If you flew on a commercial airplane at 900 kilometers per hour, it would take about 5 million years. If you rode on Voyager 1 at 17 kilometers per second, it would take about 73,000 years. If you somehow hitched a ride on the Parker Solar Probe at its closest approach to the Sun, where it reaches about 192 kilometers per second, the fastest any human-made object has ever moved, it would still take roughly 6,600 years. None of those timescales are travel times. They are civilizational lifespans. The Roman Empire lasted roughly 500 years. The entire period from the invention of the printing press to today is less than 600 years. 6,600 years ago, humans were just beginning to develop the first cities in Mesopotamia. So even our absolute fastest spacecraft, moving at a speed so extreme that it would cross the United States in about a minute and a half, would need the entire span of recorded human civilization to reach the nearest star. And that spacecraft, the Parker Solar Probe, is on a bound orbit around the Sun. It is not heading outward. Its speed is borrowed from the Sun's gravity well, and it gives it all back on the outward leg of each pass. It cannot sustain that velocity on an interstellar trajectory. This is what I mean by scale collapse. The human brain evolved to navigate landscapes measured in kilometers. We can intuitively grasp distances up to maybe a few thousand kilometers, the kind of distances you might drive across a continent. Beyond that, numbers lose their emotional weight. 1,000,000 kilometers sounds bigger than 1,000 kilometers, sure, but it does not feel proportionally bigger. It is just a bigger number, and when you get into trillions of kilometers, the feeling vanishes entirely. The number becomes abstract, meaningless, a string of digits that the brain processes as very far without any real comprehension of how far very far actually is. This is why the jump from interplanetary to interstellar travel sounds like a matter of degree when it's actually a matter of kind. Mars is about 225 million kilometers from Earth at its closest approach. Proxima Centauri is about 40 trillion kilometers away. That is not 100 times farther. It is not 1,000 times farther. It is roughly 177,000 times farther. If getting to Mars is like walking across a room, getting to Proxima Centauri is like walking from New York to Los Angeles, except you have to do it while carrying everything you will ever need. And there is no air, no ground beneath your feet, and the path is filled with radiation. And here is the thing about speed improvements that most futurist narratives conveniently ignore. The benefit of going faster does not scale linearly with the difficulty of going faster. Doubling your speed does not halve your travel time in any practical sense, because doubling your speed requires exponentially more energy, exponentially more fuel, exponentially more shielding, and it introduces entirely new categories of problems: time dilation, interstellar medium impacts, thermal management, that did not exist at lower speeds. This is not like the history of aviation, where we went from propellers to jets to supersonic flight in a few decades. That progression happened within an atmosphere, with lift, with infrastructure on the ground, with incremental refinements to a well-understood physical system. Interstellar propulsion is not a refinement. It is a different regime of physics entirely, and the gains get harder, not easier, the faster you try to go. In the 20th century, there was genuine optimism that interstellar probes were just a few decades away. The success of the Apollo program in 1969 made it feel like velocity was simply a matter of willpower and funding. If we could get to the moon in less than a decade after deciding to try, surely we could reach the stars within a generation or two. But the moon is 1.3 light seconds away. Proxima Centauri is 4.24 light years away. The ratio between those two distances is roughly 100 million to 1. The optimism of the Apollo era was not based on physics. It was based on momentum, psychological momentum, not literal velocity. And that momentum broke against the reality that the distances between stars are not merely bigger than the distances within the solar system. They are qualitatively different. They require not better rockets, but entirely different approaches to propulsion, energy, and time. Approaches that, as of today, do not exist outside of theoretical papers and conference presentations. The most publicly discussed interstellar concept in recent years is breakthrough starshot, which proposes using ground-based lasers to accelerate a gram-scale sail to roughly 20% the speed of light. At that velocity, the probe would reach Proxima Centauri in about 20 years. On paper, this sounds like a breakthrough. In practice, it faces a cascade of unsolved engineering problems, stabilizing a sail under intense laser bombardment, surviving the interstellar medium at 60,000 kilometers per second, decelerating upon arrival, which the current design does not even attempt, and transmitting usable data back to Earth from 4 light years away using a craft that weighs less than a paperclip. Breakthrough starshot is a concept. It is not a technology. And the distance between concept and technology in this case may be as wide as the distance the probe itself would have to cross. So if distance alone were the only problem, it would already be bad enough. But distance is actually not the real wall. Distance is the thing you see when you look at a star chart. The real wall is what happens when you try to move through that distance, the energy it costs, the time it takes, the way matter behaves at the speeds required. And that wall has a name. It is called the rocket equation, and it is the most important equation in the history of space travel that almost no one outside of aerospace engineering has ever heard of. Part 5. Voyager as a measurement of failure speed. Let me reframe Voyager 1 for you, because I think most people, even space enthusiasts, are thinking about it wrong. Voyager is not a mission of exploration. Not anymore. It was once. It returned extraordinary data from Jupiter and Saturn, images that changed our understanding of the outer planets. But in the context of interstellar travel, Voyager 1 is not an explorer. It is a benchmark. It is a ruler. It measures exactly how far chemical propulsion and gravity assist can take you, and the answer is not far enough. Voyager 1 was launched using a Titan III E-Centaur rocket, one of the most powerful launch vehicles available in the 1970s. After leaving Earth, it used the gravity of Jupiter to gain additional velocity, a technique called a gravity assist, where a spacecraft passes close to a massive planet and steals a tiny fraction of that planet's orbital momentum. The energy comes from the planet's motion around the Sun. The planet slows down by an imperceptible amount, and the spacecraft speeds up by a measurable amount. It is an elegant trick, but it is a trick with hard limits, because you can only borrow momentum from planets that exist along your trajectory, and the solar system only has so many massive planets in useful positions. After its flyby of Saturn in 1980, Voyager 1 had no more planets to slingshot from. It entered a purely ballistic phase, no engines firing, no course corrections, just a straight drift outward, governed entirely by its existing momentum and the gradually weakening pull of the Sun's gravity. It has been in this phase for more than 45 years. It will remain in this phase forever. There is no engine on board capable of accelerating it further. Its thrusters are attitude control only, tiny bursts designed to keep the antenna pointed at Earth, not to change speed. The plutonium-238 in its radioisotope thermoelectric generators is decaying steadily, losing about 4 watts of power per year. By approximately 2036, there will not be enough power to run any scientific instruments. Shortly after that, there will not be enough power to transmit a signal, and then Voyager 1 will go silent. Think about what happens next. After 2036, give or take, Voyager 1 becomes a mute object. It will continue drifting at 17 kilometers per second through interstellar space. No signal, no instruments, no ability to communicate with Earth. It will do this for millions of years. It will do it for billions of years. Long after human civilization has ended, however it ends, Voyager 1 will still be out there, tumbling slowly in the dark, carrying a golden record that no one will ever play, aimed at a star it will never reach. It is, in a sense, the longest-lasting human artifact, not because it was designed for permanence, but because space is empty enough to preserve it. There is no weather, no erosion, no biological decay. Just slow particle bombardment and the occasional dust grain impact. Voyager 1 will outlast every building, every monument, every written document on Earth. And it will do so in complete silence, because the technology that created it could not produce enough velocity to make the journey meaningful, or enough power to maintain communication beyond a few decades. This is what Voyager really is. Proof that chemical propulsion is an interplanetary technology, not an interstellar one. It reached the outer planets because the outer planets are within the range of chemical rockets plus gravity assists. It will never reach another star because another star is not within that range. The gap is not a gap you can close by building a slightly bigger rocket or finding a slightly better gravity assist trajectory. The gap is structural. It is a reflection of the energy density of chemical fuels versus the energy required for interstellar transit, and that ratio does not change with better engineering. Pioneer 10 and Pioneer 11, launched in 1972 and 1973, tell the same story. Both are drifting outward, both have gone silent. Pioneer 10 lost contact in January of 2003. Pioneer 11 in November of 1995. They carry plaques instead of records, simpler messages, line drawings of a man and a woman, a diagram of the solar system. They too are dead messengers, heading nowhere in particular, at speeds that render their interstellar trajectories meaningless on any human timescale. There is a pattern here, and it deserves to be stated plainly. Every object humanity has ever sent beyond the orbit of Neptune is, from an interstellar perspective, a failure. Not a failure of intent or design. Voyager and Pioneer accomplished their planetary missions brilliantly. A failure of velocity, a failure of energy. A failure that reveals, in precise numerical terms, the distance between what we can do and what interstellar travel would require. Voyager 1 travels at 1/18,000th the speed of light. A practical interstellar mission would need to travel at somewhere between 5 and 20% the speed of light, a factor of roughly 1,000 to 4,000 times faster than Voyager. That is not an incremental improvement. That is a revolution in propulsion physics that has not happened and may not ever happen. Success, in the interstellar context, looks like silence. It looks like a golden record drifting in the dark for eternity. Never heard, never found, never arriving. And if that is what success looks like, then we need to talk about what failure looks like, and whether the thing standing between us and the stars is really distance at all, or whether it is something we have even less control over, something like time itself. Part 6. The Hidden Enemy. Time, not distance. Distance is the problem everyone thinks about. It is concrete, measurable, mappable. You can draw a line between here and Proxima Centauri and say, that is 4.24 light years. But distance, by itself, is just a number. The thing that makes distance lethal is time, the amount of time it takes to cross it, and the irreversible consequences of that crossing. At 1/10, the speed of light, a velocity no human spacecraft has ever come close to achieving, a one-way trip to Proxima Centauri would take about 42 years. That is a human lifetime. Not an impossibly long time, but long enough that the person who left Earth would arrive at Proxima Centauri as an old man or woman, having spent their entire adult life in transit. At 1% the speed of light, the trip takes 424 years. At Voyager speeds, it takes 73,000 years. The relationship between speed and travel time is simple in math and devastating in practice, because each reduction in speed does not just add years, it adds generations, then civilizations, then geological epochs. But even at high fractions of light speed, time introduces problems that distance alone cannot explain. This is where Einstein enters the story. In 1905, Albert Einstein published his special theory of relativity, and one of its most counterintuitive predictions was time dilation, the idea that time passes at different rates depending on relative velocity. The faster you move relative to a stationary observer, the slower your clock ticks compared to theirs. At everyday speeds, this effect is negligible. At significant fractions of the speed of light, it becomes dramatic. If you travelled at 90% the speed of light, time on your ship would pass at roughly 44% the rate of time on Earth. A trip that took 10 years in ship time would correspond to about 23 years of Earth time. At 99% the speed of light, the dilation factor increases to roughly 7. 1 year on the ship equals 7 years on Earth. At 99.9% it climbs to over 22. These are not theoretical curiosities. They have been confirmed experimentally, most famously through observations of muon decay in cosmic rays and through precise measurements of atomic clocks flown on high-speed aircraft and placed on GPS satellites. Time dilation is real. It happens, and for interstellar travel it creates a problem that no amount of engineering can fix. The problem is this. Even if you could build a ship that travels at 99% the speed of light, the travellers on that ship would be temporarily exiled from the civilization that launched them. They would leave Earth, experience a relatively short subjective journey, perhaps a few years, and arrive at their destination to find that decades, centuries, or millennia had passed back home. The Earth they left would not exist anymore. The people who built the ship would be long dead. The language might have changed. The political structures, the cultural references, the technology, all of it would be unrecognizable. This is not a logistical inconvenience. It is an existential fracture. Interstellar travel at relativistic speeds does not just move you through space. It moves you through time, and it moves you in only one direction forward. You cannot come back to the moment you left. You cannot synchronize your experience with the civilization that launched you. The act of traveling severs the temporal connection between traveler and origin, permanently and irreversibly. And it gets worse. Communication during the journey is constrained by the speed of light. If you're 10 light years from Earth, your messages take 10 years to arrive, and the reply takes another 10 years to come back. A conversation that takes 20 years per exchange is not a conversation. It is an archive. You are not communicating with Earth. You're sending letters to a future you will never share. By the time your message arrives, the person you sent it to may be dead. The institution that received it may have been dissolved. The language you wrote it in may have drifted beyond mutual intelligibility. This phenomenon, the progressive loss of coherent connection between traveller and origin, is what some theorists call civilizational drift. Over sufficient time and distance, an interstellar traveller or colony does not remain an extension of the civilization that sent it. It becomes something else. It develops its own culture, its own language, its own priorities. It may forget why it was sent. It may reject the values of its origin. It may not even recognize the origin civilization as related to itself. And this is not speculation based on science fiction. It is extrapolation from well-documented patterns in human history. Island populations diverging from mainlands, colonial settlements developing independent identities within a few generations, isolated communities reinventing their own social structures within decades. So the hidden enemy is not distance. Distance is a coordinate. The hidden enemy is time, specifically the irreversible passage of time during transit, which fractures every connection between the departure point and the destination. Even if you solve propulsion, even if you solve energy, even if you solve biology, time still breaks the mission. Not because the travellers die, though they might, but because the concept of home dissolves during the crossing. You leave from a place, you arrive at a time, and those two things are not the same destination. This is the second layer of the trap. The first was gravity, the second is time, and neither of them is the hardest one. The hardest one is physics itself, the mathematical ceiling that governs how much energy it takes to move mass through space, and it sits directly in front of every proposed interstellar technology, like a wall with no door. Part 7. The Rocket Equation as Civilization Ceiling. In 1897, a Russian schoolteacher named Konstantin Tsiolkovsky wrote down an equation that would define the limits of space travel for the next century, and, quite possibly, for all of human history. It is called the Tsiolkovsky rocket equation, and it describes the relationship between a rocket's final velocity, its exhaust velocity, and the ratio of its initial mass to its final mass. In plain language, it tells you how fast you can go based on how much fuel you carry and how fast you can throw that fuel out the back. The equation looks deceptively simple. Delta V equals the exhaust velocity multiplied by the natural logarithm of the ratio of initial mass to final mass. Delta V is your change in velocity, how much speed you gain. Exhaust velocity is how fast your propellant leaves the engine, and the mass ratio is the total mass of the rocket at launch, divided by the mass of the rocket after all the fuel is burned. The critical word in that equation is logarithm, because the logarithm grows slowly, very slowly, and that slowness is the ceiling. Here is what it means in practice. If you want to double your delta V, you cannot just double your fuel, you have to square your mass ratio. If a mass ratio of 10 gets you to a certain speed, a mass ratio of 100 gets you to twice that speed, and a mass ratio of 10,000 gets you to 3 times that speed. The fuel requirement does not grow linearly with velocity, it grows exponentially. An exponential growth is the kind of growth that kills engineering projects, because it means that every incremental improvement in speed requires a disproportionately massive increase in fuel, which means more structural mass to hold the fuel, which means even more fuel to lift the structural mass, which means even more structural mass, and so on, in a vicious spiral that converges on impossibility. For chemical rockets, the kind that launched every mission in the history of spaceflight, the exhaust velocity is roughly 3 to 4.5 kilometers per second. That is fast by everyday standards, but pathetically slow by interstellar standards. To reach even 1% the speed of light using chemical propulsion, you would need a mass ratio so absurdly large that the fuel required would outweigh the observable universe. This is not an exaggeration. This is the math. Chemical rockets can get you to the moon. They can get you to Mars. They can, with gravity assists, get you to the outer planets. They cannot, under any conceivable configuration, get you to another star. So what about nuclear propulsion? Project Orion, conceived in the late 1950s, proposed detonating nuclear bombs behind a massive pusher plate to accelerate a spacecraft. The concept was technically feasible. It was one of the few interstellar propulsion ideas that could actually be built with existing technology, at least in principle. Freeman Dyson, one of the physicists involved, estimated that an Orion ship could reach about 3 to 5% the speed of light. At that speed, a trip to Proxima Centauri would take roughly 80 to 140 years. Not great, but conceivably within the range of a multi-generational mission. The problem is that Project Orion was killed, not by physics, but by politics. The Partial Nuclear Test Ban Treaty of 1963 prohibited nuclear detonations in space, and no government since has seriously proposed reviving the concept. There are also practical concerns. The sheer number of nuclear devices required, estimates range into the hundreds of thousands, the radiation exposure to the crew, and the engineering challenges of building a pusher plate that can survive repeated nuclear blasts at close range. Orion remains the most plausible interstellar propulsion concept ever seriously studied, and it was abandoned before it was ever tested. Project Daedalus, proposed by the British Interplanetary Society in the 1970s, took a different approach. It envisioned a fusion-powered probe that would use pellets of helium-3 and deuterium, ignited by electron beams, to achieve roughly 12% the speed of light. The trip to Barnard's star, about 6 light-years away, would take approximately 50 years. The design was elegant, but it had a fatal dependency: helium-3. There is almost no helium-3 on Earth. The proposed source was the atmosphere of Jupiter, which would require a mining infrastructure in the Jovian system that does not exist, and would itself require decades or centuries to build. Daedalus was not a mission design. It was a thought experiment that assumed access to resources we do not have and cannot currently obtain. Every proposed interstellar propulsion system runs into the same wall. You can change the fuel, you can change the engine, you can change the mass ratio, but you cannot change the rocket equation. It is a mathematical identity, as certain as 2 + 2 = 4. It says that velocity costs fuel exponentially, and no engineering trick eliminates the exponent. You can reduce it, you can shift it, but you carry your future fuel problem forward with every kilogram you add to the ship. This is the civilization ceiling. It is not a wall you can see or touch. It is a mathematical relationship between energy, mass, and velocity that limits how fast any physical object can be accelerated by expelling reaction mass. And until someone discovers a propulsion method that does not rely on reaction mass, a method that, as of today, exists only in speculative physics papers and science fiction. The rocket equation defines the boundary of what is possible. The universe permits motion. The universe does not permit cheap motion, and the cost of interstellar motion, calculated honestly, exceeds the resources of any civilization we can currently envision. Which raises the next question. If the cost is energy, how much energy are we actually talking about? Part 8. The energy nobody can afford. Let me give you a number that will reframe everything you think you know about interstellar travel. To accelerate a single kilogram of mass, not a spaceship, not a crew, just 1 kilogram, roughly the weight of a bag of flour, to 10% the speed of light requires approximately 450 terajoules of energy. That is 450 trillion joules. It is roughly equivalent to the energy released by a 100 kiloton nuclear weapon, about 6 times the yield of the bomb dropped on Hiroshima, for 1 kilogram, at 1/10 light speed. Now scale that up to a spacecraft. Even a interstellar interstellar probe, something like the 100-kilogram microsatellites we currently use in Earth orbit, would require 45,000 terajoules to reach 10% light speed. That is equivalent to the annual electricity consumption of a small country. For a crewed vessel massing thousands of tons, the energy requirement enters the realm of planetary scale or stellar scale energy budgets. To accelerate a 1,000-ton ship to 10% light speed would require roughly 4.5 times 10 to the 20th joules, about 1% of the total energy output of the sun in a single second. Sounds manageable, maybe, until you realize you also need to decelerate at the other end, which doubles the energy requirement, and you need to carry the deceleration fuel with you, which invokes the rocket equation again, which multiplies the energy requirement yet again. The most energy-dense fuel known to physics is antimatter. When a particle of matter meets its corresponding antiparticle, they annihilate completely, converting 100% of their combined mass into energy via Einstein's E equals mc squared. No chemical fuel comes close. No nuclear fuel comes close. Antimatter is the theoretical ceiling of energy storage density, and as of 2026, the total amount of antimatter ever produced by all particle accelerators on Earth combined is measured in nanograms, a few billionths of a gram. The cost of producing antimatter at current facilities has been estimated by NASA at roughly $62.5 trillion per gram. The amount needed to fuel even a small interstellar probe would be measured in tons. The gap between what we can produce and what we would need is not a gap. It is a chasm wider than the one we are trying to cross. Fusion is the other candidate usually mentioned. The Sun runs on fusion, hydrogen nuclei combining to form helium, releasing energy in the process. If we could build a fusion reactor compact enough and powerful enough for a spacecraft, it would offer energy densities far beyond chemical or fission fuels. The problem is that we have been trying to build a sustained net positive fusion reactor since the 1950s, and as of today we have not achieved one that produces more energy than it consumes over sustained periods. ITER, the International Fusion Experiment under construction in France, is designed to demonstrate net positive fusion, but it is a building-sized facility, not a spacecraft engine, and even if it succeeds, the engineering path from a ground-based reactor to a flight-rated interstellar propulsion system is measured in decades to centuries, if it is achievable at all. And then there is the thermodynamic problem that almost never gets discussed in popular accounts of interstellar travel. In space, there is no air. That means there is no convection, no way to shed waste heat by blowing it away. The only mechanism for cooling in a vacuum is radiation, emitting infrared photons from large surface areas. Any engine powerful enough to accelerate a ship to interstellar velocities will produce enormous amounts of waste heat, and that heat has to go somewhere. The radiator surfaces required to manage this thermal load scale, with the power output of the engine, and for interstellar class propulsion, those radiators become enormous, potentially larger than the ship itself. You end up designing a spacecraft that is mostly radiator, with a small payload tucked inside, which increases mass, which increases fuel requirements, which circles back to the rocket equation. This is the core paradox. The energy required for interstellar travel exists in the universe. The Sun outputs more than enough energy every second to accelerate a fleet of starships. But that energy is not available in a form we can capture, store, and direct. Sunlight is diffuse, nuclear fuels are limited, antimatter is essentially non-existent in producible quantities. Fusion is uncontained. The energy is there in principle and inaccessible in practice. The universe is full of energy the way an ocean is full of water, surrounding you completely and completely useless if you do not have a cup. This is not a problem of funding or willpower, this is a problem of physics, and it sits on top of the distance problem and the time problem like a third layer of a lock that has no key, at least no key we have found in over a century of looking. Part 9. The myth of eventually we scale up. There is a comforting story we tell ourselves about technology. It goes like this. Every problem that once seemed impossible eventually became trivial. Humans could not fly, and then we flew. We could not split the atom, and then we split it. We could not reach the moon, and then we reached it. Therefore, interstellar travel is just the next item on the list. Give it enough time, enough investment, enough ingenuity, and we will get there. This story is seductive. It is also, I think, dangerously misleading. The history of technology does contain genuine breakthroughs, transitions from impossible to routine. But it also contains plateaus, technologies that reached a ceiling and stopped. The internal combustion engine has been refined for over a century, but its fundamental efficiency has not doubled in the last 50 years. Commercial aircraft fly at roughly the same speed today as they did in the 1960s. Nuclear fission reactors produce energy at roughly the same temperatures and efficiencies they did in the 1970s. The Concorde, which flew passengers at twice the speed of sound, was retired in 2003 and has not been replaced. Not every technological curve goes up forever. Some of them flatten, some of them stop, and the ones that stop tend to be the ones that run into fundamental physical limits, rather than mere engineering challenges. Rocket propulsion is one of those technologies. Chemical rocket engines today are not dramatically more efficient than the engines used in the Apollo program. The Space Shuttle main engines were marvels of engineering, but their specific impulse, a measure of fuel efficiency, was only modestly better than the J2 engines that powered the Saturn V's upper stage in the 1960s. The reason is not lack of effort. The reason is that chemical combustion has a maximum energy yield, dictated by the bond energies of the molecules involved, and we are already operating close to that maximum. You cannot make a hydrogen-oxygen rocket dramatically more efficient, because the energy stored in the chemical bonds of hydrogen and oxygen is a fixed quantity. You can extract it more cleanly, but you cannot increase it. The same ceiling exists at a higher level for nuclear propulsion and at an even higher level for fusion, and at the theoretical maximum for antimatter. Each fuel type offers more energy per kilogram, but each also comes with its own set of engineering constraints, material requirements, and scaling problems. And critically, the energy demands of interstellar travel grow exponentially with velocity, while civilizational energy production grows, at best, linearly or polynomially over time. These two curves, exponential demand and linear supply, do not intersect at any point in any realistic projection of human technological development. There is also the coordination problem. Building an interstellar spacecraft is not like building a bridge or a skyscraper. It would be the largest, most complex, most expensive single engineering project in human history, by many orders of magnitude. It would require sustained investment over decades or centuries, across political boundaries, through economic cycles, wars, and social upheavals. The International Space Station, one of the most ambitious cooperative projects ever attempted, took over 2 decades to build and cost roughly $150 billion, and it orbits just 400 kilometers above the Earth. An interstellar ship would need to be orders of magnitude larger, more durable, and more self-sufficient, and it would need to function without resupply or repair for decades at minimum. The political and economic stability required to execute such a project does not currently exist on Earth, and has never existed in human history. So the idea that eventually we scale up is not a prediction, it is an assumption that technological progress is monotonic, that every barrier eventually yields, that exponential curves always meet somewhere over the horizon. But physics does not make that guarantee. Physics says that some things are hard and some things are impossible, and the difference between the two is not always visible from where we are standing. The claim at the center of this story, that humanity may never leave the solar system, is not a claim about pessimism or defeatism. It is a claim about mathematics, about the specific, quantifiable, testable relationship between energy, mass, velocity, and time. And that relationship, as far as we can currently tell, does not have a solution that fits within the envelope of any civilization we can plausibly imagine. But even if it did, even if some miracle of physics handed us a working interstellar engine tomorrow, there would still be another wall. A wall made not of equations, but of biology. Because the engine is not the weakest link in any interstellar mission. The crew is. Part 10. Space is hostile to bodies, not just machines. The International Space Station orbits Earth at an altitude of about 400 kilometers. It is well within the protection of Earth's magnetosphere, the magnetic field that deflects the majority of incoming charged particles from the Sun and from deep space. Even so, Astronauts on the ISS receive about 200 to 300 millisieverts of radiation per year, roughly 100 times the annual dose of an average person on the ground. NASA has career radiation exposure limits for astronauts, calibrated to keep the increased risk of cancer below 3%. A typical 6-month ISS mission uses up a significant fraction of that career allowance. Now imagine leaving the magnetosphere entirely. Beyond Earth's protective field and beyond the heliosphere's more diffuse shielding, the radiation environment changes dramatically. Galactic cosmic rays, high-energy protons and atomic nuclei from supernovae and other violent astrophysical events pervade interstellar space. These particles carry so much energy that they can penetrate several meters of solid material. They pass through spacecraft hulls, through human tissue, through bone, shattering DNA strands as they go. The damage is cumulative and largely irreparable over long time periods. On a multi-decade or multi-century interstellar mission, the crew would be subjected to chronic, unshielded cosmic ray bombardment that exceeds every radiation safety limit ever established by any space agency. Shielding helps, but not as much as you might think. Water, polyethylene, and other hydrogen-rich materials are among the best cosmic ray shields. But even several meters of such material only reduces the dose, it does not eliminate it. And adding shielding adds mass, which adds fuel requirements, which circles back to the rocket equation. Every kilogram of radiation shielding requires additional fuel to accelerate and decelerate, which requires additional structural mass, which requires additional fuel. The protection of the crew competes directly with the propulsion budget, and in a system governed by exponential scaling, that competition has no clean resolution. Then there is microgravity. The human body evolved under 1G, the gravitational pull at Earth's surface. Remove that pull, and the body begins to deteriorate in ways that are still not fully understood. Muscle atrophy begins within days. Bone density decreases at a rate of about 1 to 2% per month, faster than postmenopausal osteoporosis. Cardiovascular deconditioning occurs as the heart no longer needs to pump blood upward against gravity, leading to changes in blood pressure regulation and increased risk of cardiac events. Cerebrospinal fluid redistributes, increasing intracranial pressure and causing vision problems, a condition now formally recognized as spaceflight-associated neuroocular syndrome. ISS astronauts exercise for about 2 hours every day using specialized equipment, and they still experience measurable bone loss and muscle atrophy during 6-month missions. Some of these changes are partially reversible after return to Earth, some are not. And these are healthy, rigorously screened adults in their physical prime on missions lasting 6 months, with full medical support and the option of emergency return. An interstellar crew would be in microgravity, or at best in some form of artificial gravity, itself an unsolved engineering problem for decades, with no option to return, no hospital, and no evacuation route. The human body is not a vacuum-compatible system. It is a warm, wet, oxygen-dependent, gravity-calibrated biological machine that evolved specifically for conditions on the surface of Earth. Every aspect of space, the vacuum, the radiation, the absence of gravity, the temperature extremes, is actively hostile to it. This is not a metaphor. The hostility is physical, measurable, and cumulative, and it places a biological timer on any interstellar mission that no propulsion system can outrun, because the longer the journey takes, the more damage the crew accumulates, and the less likely they are to arrive in any condition to accomplish anything. This is the wall that rarely makes the headlines. Everyone talks about engines and fuel. Almost no one talks about the fact that the passengers are slowly being destroyed by the environment they are travelling through, and if you cannot keep the passengers alive and functional, then the engine does not matter. The fuel does not matter. The destination does not matter. The mission fails from the inside out. So the natural response is, build a self-sustaining ship, grow food on board, recycle everything, create a closed ecosystem that can operate independently for the duration of the journey. It sounds reasonable. It has been tried, and every single attempt has failed. Part 11. Closed worlds always fail. In 1991, 8 people walked into a 3.14-acre glass and steel structure in Oracle, Arizona, called Biosphere 2. The facility was designed to be a completely sealed, self-sustaining ecosystem, a miniature Earth containing a rainforest, an ocean, a desert, agricultural land, and a habitat for the crew. The idea was to test whether humans could survive inside a closed life support system with no external inputs. The answer, delivered over 2 agonizing years, was no. Within the first 16 months, oxygen levels inside Biosphere 2 dropped from 20.9% to 14.5%, equivalent to the oxygen concentration at an altitude of about 4,300 meters, roughly the height of some Rocky Mountain peaks. The crew experienced chronic fatigue, impaired cognitive function, and difficulty performing physical tasks. The cause was eventually traced to an unexpected interaction between soil microbes and the concrete structure. Microorganisms were consuming oxygen and producing carbon dioxide at a rate the designers had not anticipated, and the carbon dioxide was reacting with exposed concrete, effectively sequestering it and preventing the expected carbon cycle from closing. The agricultural system underperformed, producing less food than projected. Crew members lost an average of 16% of their body weight. Social tensions escalated, eventually splitting the group into factions that barely spoke to each other. Insects that were supposed to pollinate crops died off. Cockroaches and ants, unbothered by the conditions, thrived. The morning glory vines, introduced as a decorative element, became invasive and began choking out other plants. The ocean's coral reef died. The system did not collapse all at once. It degraded unpredictably through cascading feedback loops that no one had modelled because no one knew they existed. Biosphere 2 was not a failure of engineering in the traditional sense. The structure was well built. The systems were thoughtfully designed. The failure was ecological, a failure to predict the behaviour of thousands of interacting biological and chemical systems operating in a sealed environment over time. And this is the key insight. A closed-loop life support system is not an engineering problem. It is an ecological equilibrium problem. And ecological equilibria are notoriously unstable, non-linear, and sensitive to initial conditions. Earth itself is a closed-loop life support system, the only one known to work. It has been running for roughly 4.5 billion years, stabilized by processes operating at planetary scale. Oceanic circulation, atmospheric chemistry, plate tectonics, the water cycle, the carbon cycle, the nitrogen cycle. These systems are massive, redundant, and self-correcting in ways that no artificial habitat can replicate. The idea that we could reproduce them inside a spacecraft at a fraction of the scale, with no margin for error, for decades or centuries, is not just optimistic. It is, based on every experiment conducted to date, unsupported by evidence. Every sealed habitat experiment since Biosphere 2 has confirmed the same pattern. Small perturbations, a microbial bloom, a crop failure, a chemical imbalance cascade through the system in ways that are difficult to predict and often impossible to reverse without external intervention. The BIOS 3 experiments in the Soviet Union during the 1970s and 80s achieved partial closure but required significant external inputs. The Melissa project by the European Space Agency, ongoing since the 1980s, has made progress on individual subsystems, algae-based air recycling, plant growth chambers, but has not yet demonstrated a fully closed loop at any scale. And this connects directly to why leaving the solar system is not merely an engineering challenge. Because any interstellar mission longer than a few years, and most realistic interstellar missions would last decades, centuries, or millennia, requires a life support system that functions as a self-sustaining ecosystem. Not a machine, an ecosystem. and we have never successfully built one, not once, not even for 2 years. Not even on Earth, where we had the advantage of gravity, sunlight, external power, and the ability to open a door and walk out if things went wrong. Aboard a starship, there is no door to open. There is no external resupply. There is no rescue mission. If the oxygen drops, if the crops fail, if the water recycling system develops a microbial contamination, if the social structure of the crew collapses, there is nothing outside. The closest help is light years away, and the message asking for it takes years to arrive. A closed-world ship is not a vehicle. It is a terrarium hurtling through a vacuum at a significant fraction of the speed of light, and every terrarium ever built has eventually failed. Part 12. The ship becomes a civilization. If you cannot get to the stars in a single human lifetime, the obvious alternative is a generation ship, a vessel large enough to sustain a human population for centuries or millennia, with each generation born, raised, and dying aboard the ship, passing the mission forward to their descendants. It is one of the oldest ideas in science fiction, and on the surface it sounds almost plausible. Build the ship big enough, stock it well enough, design the systems carefully enough, and let human reproduction do the rest. The numbers, however, are brutal. Population geneticists have estimated that a minimum viable population for a multi-generational space voyage would need to be somewhere between 5,000 and 40,000 individuals, depending on assumptions about genetic management, reproductive policy, and acceptable levels of inbreeding. Smaller populations risk genetic bottleneck effects, reduced genetic diversity leading to increased susceptibility to disease, reduced fertility, and accumulation of harmful recessive alleles. The Polynesian colonization of the Pacific Islands provides a rough analogue. Populations that were too small experienced genetic drift, health problems, and in some cases, extinction. But genetic diversity is only the beginning of the problem. A generation ship carrying 10,000 people for a 1,000-year journey is not a spacecraft. It is a civilization. It needs governance, laws, education, social institutions, dispute resolution mechanisms, cultural transmission systems, and some form of economy. It needs to manage reproduction, not just for genetic health, but to maintain population size within the carrying capacity of the ship's life support systems. It needs to train each new generation in the technical skills required to maintain the ship, while simultaneously transmitting the mission's purpose across centuries of cultural evolution. And this is where the thought experiment breaks down, because human civilizations do not hold steady over millennial timescales. They transform, they fragment, they forget. Languages mutate. Old English is unreadable to modern English speakers, and that divergence occurred in less than 1,000 years, on a continuous landmass with constant cultural exchange. On an isolated ship with a population of 10,000, linguistic drift would occur faster, not slower. Within a few centuries, the original mission language might be unintelligible to the current generation. Cultural values would shift as well. The first generation would understand the mission. They would remember Earth, feel connected to its purpose, carry the emotional weight of leaving. The second generation would have heard stories. The third would have heard stories about stories. By the 10th generation, the departure from Earth would be mythology, a founding narrative no more empirically real to the living crew than the Trojan War is to a modern Greek. The mission might persist as ritual, as tradition, as cargo cult. Or it might be rejected entirely, replaced by a new ideology born of the ship's own internal politics and cultural evolution. History offers uncomfortable parallels. Isolated communities routinely develop governance structures, belief systems, and social hierarchies that diverge radically from their parent cultures within just a few generations. The Pitcairn Islanders, descended from the HMS Bounty mutineers, developed their own dialect and social structure within decades of settlement. The various Polynesian cultures, originating from a common ancestral population, diverged into markedly different societies across the Pacific within centuries. A generation ship would be more isolated than any island ever was, and the timescales involved would be much longer. The ship does not stay a ship, it becomes a world, and the people on it do not stay a crew. They become a civilization, with all the instability, unpredictability and tendency toward transformation that the word implies. The mission planners on Earth might design the ship for a specific destination and a specific purpose. By the time the ship arrives, neither the destination nor the purpose may matter to the people on board. They may have no desire to colonize a new world. They may have no memory of why they left the old one. The ship is their world. It has always been their world. And the idea that they were sent here by people who lived on a planet called Earth may sound to them exactly the way ancient myths sound to us. Interesting, perhaps, but not binding, not real, not relevant. This is the final biological wall. Not radiation, not ecosystem failure, not genetic bottleneck, though all of those are real. The final wall is cultural. Interstellar travel at sublight speeds requires multi-generational continuity, and multi-generational continuity is something human civilizations have never achieved. Not even on Earth, not even under ideal conditions. The mission does not fail because the ship breaks. It fails because the civilization inside the ship transforms into something the mission planners never imagined and cannot control. And all of this, the gravity, the distance, the time, the energy, the biology, the sociology, is still only part of the problem. Because the universe has its own objections to interstellar travel, and they are not passive. They are active, physical, and getting worse. Part 13. Relativity as psychological separation. We talked about time dilation earlier as a physics problem. Now let me talk about it as a human problem, because the psychological and civilizational consequences of relativistic travel are, in some ways, more devastating than the physical ones. Imagine you were a crew member on a ship travelling at 90% the speed of light toward a star system 10 light-years away. From your perspective, the journey takes about 4.4 years. You eat, sleep, work, maintain the ship. You watch movies, argue with your crewmates, celebrate birthdays. You arrive at the destination feeling like you have been in transit for a bit over 4 years. But when you look back at Earth, when you aim your antenna homeward and listen for a signal, you learn that 23 years have passed there. Everyone you knew has aged by more than 2 decades. Your children, if you had any, are adults. Your parents may be dead. The political landscape has changed. The technology has advanced. The culture has shifted. You left one world and arrived in another, and the version of Earth you carry in your memory no longer exists. Now, scale that up. A ship travelling at 99%. The speed of light experiences a time dilation factor of roughly 7 to 1. A subjective journey of 5 years corresponds to 35 years of Earth time. At 99.9%, the factor rises to about 22. 5 subjective years equals 110 years of Earth time. Everyone you ever knew is dead. The institutions that built your ship may have been dissolved. The language of your mission briefing may have become archaic. You're not a traveller returning from a long trip. You're a visitor from the past, arriving in a future that did not wait for you. This is not an abstract concern. It is arguably the single most destructive consequence of near-light speed travel, because it means that interstellar missions are inherently one way, not just in the spatial sense, but in the temporal sense. You cannot go home. Not because home is far away, but because home is in the past, and the past is not a place you can return to. Even if you turn the ship around and fly back to Earth at the same speed, more time will have passed. You arrive in an even more distant future. The round trip does not restore you to your origin, it doubles your exile. Relativistic travel, if it were ever achieved, would not connect civilizations, it would sever them. Every ship that left would become an island in time, drifting forward through centuries at a different rate than the world it departed from. communication would be possible in the same way that sending a letter into a time capsule is possible. You can write it, you can send it, but you cannot have a conversation. The speed of light limits not just the velocity of travel, but the velocity of information, and information that takes decades to exchange is not communication. It is broadcast. Some theorists have suggested that this would not matter, that interstellar colonies, once established, would function independently, free of the need for real-time connection to Earth. And that is probably true. But it also means that interstellar travel does not extend a civilization. It ends one and begins another. The colony is not an outpost of Earth. It is a separate entity, born from Earth but no longer part of it, evolving independently, making its own choices, forgetting its own origins. If that is the outcome, then interstellar travel does not solve the confinement problem. It merely replicates it, creating new isolated systems that are, themselves, trapped around new stars, facing the same barriers all over again. Part 14. The interstellar medium becomes a weapon. There is a persistent misconception that space is empty. It is not. The space between stars contains matter, not much, by terrestrial standards, but enough to matter enormously at high velocities. The interstellar medium consists primarily of hydrogen atoms, at a density of roughly 1 atom per cubic centimetre. There are also dust grains, microscopic particles of silicate and carbon, ranging from nanometers to micrometers in size. At everyday speeds, this material is harmless. At interstellar speeds, it becomes a weapon. Consider a spacecraft travelling at 10% the speed of light, 30,000 kilometers per second. At that velocity, a single hydrogen atom, with a mass of about 1.7 times 10 to the negative 27 kilograms, carries kinetic energy equivalent to about 7.7 times 10 to the negative 16 joules. That sounds tiny, and it is, for one atom. But the interstellar medium contains roughly 1 atom per cubic centimetre. A spacecraft with a cross-sectional area of 10 square metres, travelling at 10% light speed, would sweep up approximately 3 times 10 to the 13 hydrogen atoms per second. The cumulative energy deposition is equivalent to continuous bombardment by high-energy particle radiation. It would erode surface materials, degrade sensors and optical systems, and deliver radiation doses to any crew or electronics behind the hull. Dust grains are far worse. A single interstellar dust particle, even one just a micrometer in diameter, weighing about 1/trillionth of a gram, striking a spacecraft at 10% light speed, carries kinetic energy roughly equivalent to a small caliber bullet. At higher speeds, the energy scales as the square of velocity. At 50% light speed, each micrometer dust grain hits with the energy of a hand grenade. At 90% light speed, the energy per particle reaches levels comparable to explosive ordnance. This is why just go faster is not a solution. Speed creates its own problems. The faster you travel, the more energetic each particle impact becomes, and the more shielding you need to protect the spacecraft and its contents. But shielding adds mass, which adds fuel, which invokes the rocket equation, which demands more energy, which cycles back to the propulsion problem. It is another closed loop, another layer of the trap where solving one problem worsens another. Breakthrough Starshot, the laser-propelled light cell concept, faces this problem acutely. Its proposed probe would travel at roughly 20% the speed of light, but it would weigh less than a gram. It would have no shielding to speak of. Over a 4-year transit to Proxima Centauri, it would accumulate thousands of dust grain impacts, each one potentially catastrophic for a device the size and thickness of a postage stamp. The Starshot team has acknowledged this challenge and has proposed various mitigation strategies: aerodynamic shaping of the sail, sacrificial surface layers, but none have been tested, and the physics of high-velocity particle impact is not fully understood at the speeds involved. Even at lower velocities, say 1% the speed of light, which is well below the threshold for useful interstellar transit times, Particle impacts pose engineering challenges that have no current solutions. Spacecraft surfaces would erode, sensors would degrade. Over decades-long missions, cumulative damage would reduce functionality in ways that cannot be repaired in transit. The interstellar medium is not a passive background. It is an active obstacle, and its hostility scales directly with the speed of the craft, the same speed that is essential for making the journey feasible in the first place. The universe has arranged things so that the solution to one problem, go faster to reduce transit time, directly creates another problem, increased particle bombardment. This is not an accident. It is a consequence of the fact that kinetic energy scales with the square of velocity, while the interstellar medium exists everywhere, thinly but uniformly between the stars. You cannot avoid it. You can only absorb it, and absorbing it costs mass, which costs fuel, which costs energy, which brings you back to the same wall you started at. Part 15. The universe is actively reducing our options. Everything we have discussed so far, distance, time, energy, biology, the interstellar medium, operates within a static universe. But the universe is not static, it is expanding, and the expansion is accelerating. In 1998, two independent teams of astronomers, the Supernova Cosmology Project and the High Z Supernova Search Team, discovered that the expansion of the universe is not slowing down, as most physicists had expected. It is speeding up. Distant galaxies are receding from us at velocities that increase with distance, driven by a mysterious repulsive force now called dark energy, which constitutes roughly 68% of the total energy content of the universe. This discovery, which earned the 2011 Nobel Prize in Physics, fundamentally changed our understanding of the long-term future of the cosmos. The Hubble flow, the name given to the general recession of galaxies due to cosmic expansion, means that the distance between unbound objects in the universe is continuously increasing. And because the expansion is accelerating, the rate of increase is itself increasing. Galaxies that are currently visible in our telescopes are, at this very moment, moving away from us faster than they were 1 billion years ago, and they will be moving away even faster 1 billion years from now. This has a consequence that is rarely discussed outside of cosmology, but is directly relevant to interstellar travel and the long-term fate of any spacefaring civilization. There is a cosmic event horizon, a boundary beyond which objects are receding from us faster than the speed of light. This is possible because the speed limit of special relativity applies to objects moving through space, not to the expansion of space itself. Space itself can expand faster than light, carrying galaxies along with it like dots on an inflating balloon. Objects beyond the cosmic event horizon are, by definition, unreachable. No signal, no spacecraft, no beam of light sent toward them today will ever arrive, because the space between us and them is growing faster than anything can cross it. The current estimated radius of our cosmic event horizon is roughly 16 billion light-years. That sounds like a lot, and it is. But here is the disturbing part. The number of galaxies beyond that horizon is growing. Every second, roughly 20,000 galaxies cross the event horizon and become permanently unreachable. They do not disappear. They do not cease to exist. They simply move beyond the boundary from which any signal or object could ever return. They are lost to us, not through distance, but through the expansion of the medium that distance is measured in. This creates a temporal urgency paradox that most discussions of interstellar travel ignore entirely. Every year that passes without achieving interstellar capability is a year in which the reachable universe gets smaller. Not by much. The effect is negligible on timescales of centuries or even millions of years for objects within our own galaxy. The Milky Way is gravitationally bound, and galaxies in our local group will remain accessible regardless of cosmic expansion. But on longer timescales, billions of years, the consequences are profound. The Milky Way and Andromeda will merge in roughly 4.5 billion years, forming a single galaxy. But beyond the local group, Everything else will have receded beyond the event horizon. A civilization born in that future galaxy would see nothing outside it. No other galaxies, no cosmic microwave background, no evidence that the universe was ever anything other than a single island of stars floating in an otherwise empty void. The universe is not just difficult to traverse. It is actively shrinking the menu of places that can ever be traversed to. If you are trapped inside your solar system today, waiting for the technology to escape, you're also watching the universe contract around you, not physically, but causally. The set of destinations that are even theoretically reachable is smaller now than it was 1 billion years ago, and it will be smaller still 1 billion years from now. Time is not on your side. The clock is running in both directions. You do not have enough technology today, and you will have fewer options tomorrow. This is perhaps the most existentially unsettling layer of the trap. Not that the universe is large and hard to cross, but that it is getting harder to cross with every passing moment. The doors are closing. Not slamming, closing slowly, silently, on cosmological timescales that make the process invisible to any single generation, but closing nonetheless. And if you are a civilization that has not yet figured out how to leave its home system, the universe is patiently, quietly, reducing the number of places you could leave to. Part 16. The Silence Problem Reframed. In 1950, the physicist Enrico Fermi was having lunch with colleagues at Los Alamos National Laboratory when the conversation turned to the possibility of extraterrestrial civilizations. The context matters here. This was Los Alamos, the place where the atomic bomb had been built just 5 years earlier. The people sitting at that table were not dreamers. They were the most accomplished physicists on the planet, men who had already demonstrated that human intelligence could unlock the fundamental forces of nature and reshape the world in an afternoon. If anyone had earned the right to speculate about what other intelligent civilizations might accomplish, it was this group. The argument that sparked the conversation was straightforward, and it went something like this. The Milky Way galaxy is roughly 13 billion years old. It contains somewhere between 100 billion and 400 billion stars. Even if only a tiny fraction of those stars have planets, and only a tiny fraction of those planets develop life, and only a tiny fraction of that life develops intelligence and technology, the numbers are so large that the result should still be enormous. Thousands of civilizations, maybe millions. And here is the critical part. The galaxy is old enough that even a single one of those civilizations, expanding outward at a modest fraction of the speed of light, could have colonized the entire Milky Way in a few million years. That sounds like a long time, but it is not. A few million years is less than 1/10 of 1% of the galaxy's age. It is a rounding error on cosmic timescales. The galaxy has had enough time for this to happen not once, but thousands of times over. Yet there was no evidence of it. No radio signals from distant civilizations. No enormous engineering projects visible around nearby stars. No probes parked in our solar system. No signs, anywhere, that anyone had ever done what the math said should have happened many times already. Fermi reportedly looked up from his lunch and asked a question so simple it has tormented physicists ever since. Where is everybody? That question, now known as the Fermi paradox, has haunted astrophysics for more than 70 years. It is not a technical puzzle, it is an existential one. Because the silence it points to is not the silence of an empty room. It is the silence of a room that should be full. Hundreds of proposed solutions have been offered over the decades, and they range from the perfectly mundane to the genuinely unsettling. Some suggest we are simply not looking hard enough, that our radio telescopes are not sensitive enough, or that we are searching on the wrong frequencies, or that alien civilizations communicate using methods we have not thought of yet. Some suggest that intelligent life is far rarer than the numbers imply, that the conditions required for complex biology are so specific that we may be one of very few civilizations in the galaxy, or even the only one. Some suggest that civilizations arise regularly but destroy themselves before achieving interstellar capability through nuclear war, ecological collapse, artificial intelligence run amok, or some other self-inflicted catastrophe. And some suggest something more deliberate, that advanced civilizations are out there, watching but choosing not to make contact, the so-called zoo hypothesis, in which Earth is essentially a nature reserve being observed from a distance by beings who have decided not to interfere. Each of these explanations has its proponents, and none of them has been ruled out. But none of them has been confirmed either. The silence persists. In 1961, the astronomer Frank Drake tried to formalize the question by writing an equation. The Drake equation takes the rate of star formation in the galaxy and multiplies it by a chain of conditional probabilities, the fraction of stars with planetary systems, the fraction of those planets that could support life, the fraction on which life actually develops, the fraction where life produces intelligence, the fraction where intelligence builds detectable technology, and the average length of time such a civilization remains detectable. Multiply all of these together and you get an estimate of the number of communicating civilizations in the galaxy right now. The problem with the Drake equation is not that it is wrong. It is that it is empty. We do not know the values of most of its variables. The fraction of planets that develop life. We have exactly one data point, Earth. The fraction of life that produces intelligence, same data point. The average lifespan of a technological civilization. We have been one for roughly a century. That is not enough to estimate anything. The Drake equation is a framework for organizing our ignorance, not a tool for resolving it. Depending on the numbers you plug in, and reasonable scientists have plugged in wildly different numbers, the equation can output anything from 0 civilizations to 10 million. It tells us what we need to know, not what we actually know. But here is the thing. The Fermi paradox does not require the Drake equation to be troubling. You do not need to estimate the number of civilizations. You just need to accept two premises. First, that the galaxy is old enough for interstellar colonization to have occurred. And second, that it apparently has not occurred, or at least not in any way we can detect. Those two premises taken together imply that something stops civilizations from spreading, something filters them out. And the question that keeps physicists awake at night is whether that filter is behind us, some rare event in our evolutionary past that most civilizations never get through, or ahead of us, some barrier that advanced civilizations inevitably hit and fail to cross. The SETI program, the search for extraterrestrial intelligence, has been the most sustained effort to answer this question observationally. Since the early 1960s, radio telescopes around the world have been scanning the sky for artificial signals, narrowband transmissions, regular pulses, anything that looks like it was made on purpose, rather than produced by a natural astrophysical process. The effort has been heroic. It has also been, by any honest measure, a failure. In more than 6 decades of searching, SETI has detected nothing confirmed as non-natural. No candidate signal has survived follow-up observation. No laser pulse from a distant star system. No infrared excess around a nearby star that might indicate a Dyson sphere or other megastructure. The sky, at every wavelength we have checked, is quiet. Now, this silence is not definitive. Our search has been limited in ways that matter. We have surveyed only a tiny fraction of the sky at high sensitivity. We have focused primarily on radio frequencies, which may not be the preferred communication method of an advanced civilization. We have looked for continuous signals when the actual transmission might be brief or directional. There are legitimate reasons why we might have missed something, but the absence of detection, after 60 years of looking, is at the very least suggestive. If the galaxy were teeming with expansive communicative civilizations, we would expect some evidence of their activity by now, and we have found none. There is a hypothesis embedded in this silence that connects directly to everything we have discussed in this story: the distance, the energy, the time, the biology, the rocket equation, the interstellar medium, the expanding universe. What if the silence is not a mystery? What if it is a prediction? What if the reason we see no evidence of interstellar civilizations is that interstellar travel is, for physical rather than technological reasons, effectively impossible? Not merely difficult, not merely expensive, not merely beyond our current capabilities, awaiting some future breakthrough, but structurally incompatible with the constraints that govern matter, energy, and time in this universe. If that is true, then every civilization that arises around a star, every species that develops language and mathematics and radio telescopes and dreams of crossing the void, is confined to its home system, permanently, not because it is not smart enough to leave, not because it did not try hard enough, but because the physics will not allow it. If that is the case, then the Fermi paradox is not a paradox at all. It is the expected result. A galaxy full of intelligent civilizations, each one trapped in its own stellar system, each one scanning the sky and hearing nothing, each one asking the same question Fermi asked, "Where is everybody?" and slowly realizing that everybody is right where they started, looking outward through telescopes at a universe they can map but never cross. This is a different kind of answer to Fermi's question, and it is one that most discussions avoid because it is genuinely uncomfortable. We want to believe that the stars are reachable. We want to believe that intelligence, given enough time, confers the ability to overcome any physical constraint. We have built an entire cultural mythology around the idea that humanity's destiny is out there, among the stars, waiting for us to grow up enough to claim it. Every science fiction franchise, every space agency mission statement, every inspirational poster of a rocket silhouetted against a galaxy, all of it rests on the assumption that the cage has a door. But what if it does not? What if intelligence allows you to understand the cage perfectly, to map every bar, to measure every wall, to calculate the exact energy required to break through? And the answer, every time, for every civilization, is that the bars are stronger than anything you can build. What if the final gift of intelligence is not escape, but comprehension, a complete, precise, mathematically certain understanding of why escape is not possible? That is the version of the Fermi paradox that no one puts on a poster. And it is the version that the physics, as we currently understand it, most strongly supports. Part 17. The stack of impossible constraints. Let me lay out the full architecture of the problem because I think seeing it all at once matters. We have spent this entire journey examining individual walls, distance, energy, time, biology, the interstellar medium, the expanding universe. Each one, on its own, is formidable. But the real reason interstellar travel may be impossible is not any single wall. It is the fact that all of them exist simultaneously, and they are connected to each other in ways that make solving one problem actively worse for another. To travel from our solar system to even the nearest star, a civilization must simultaneously solve all of the following. It must accelerate a vessel to a significant fraction of the speed of light, which requires energy on a scale no known technology can provide, energy equivalent to the annual output of entire nations, concentrated into a single propulsion system and sustained for months or years. It must carry or generate fuel sufficient for both acceleration and deceleration, which the Tsiolkovsky rocket equation makes exponentially expensive, not linearly expensive, not merely difficult but exponentially scaling, meaning every incremental increase in speed requires a disproportionately massive increase in fuel, which requires more structural mass, which requires even more fuel. It must protect the crew or payload from interstellar medium bombardment at relativistic speeds, because at 10 or 20% the speed of light, individual hydrogen atoms hit with the energy of cosmic rays and dust grains hit with the energy of bullets or small explosives, and shielding against this bombardment requires mass. Mass that compounds the fuel problem, feeding directly back into the rocket equation. It must sustain a biological crew for decades to millennia inside a closed-loop ecosystem that has never been successfully demonstrated at any scale. Not even for 2 years. Not even on Earth. Not even with unlimited external power and the option of opening a door and walking out when things went wrong. It must manage the psychological, sociological and genetic consequences of multi-generational isolation without civilizational collapse, maintaining governance, cultural continuity, technical knowledge and mission purpose across centuries of confinement inside a metal shell, with no external contact and no possibility of rescue. It must maintain communication with the origin civilization across light-year distances and decades-long signal delays, which means that any conversation between ship and home takes years per exchange, rendering real-time coordination impossible and reducing the connection between traveller and origin to something closer to archaeology than dialogue. And it must accept that time dilation, an unavoidable consequence of relativistic velocity, will sever any meaningful temporal connection between the travellers and the world they left, so that even if the mission succeeds, the travellers arrive in a future that bears no resemblance to the past they departed from. That is 7 simultaneous requirements, not 7 sequential steps where you complete one and move to the next. 7 interlocking constraints that must all be satisfied at the same time, by the same vehicle, on the same mission, with the same budget of mass, energy and time. And here is what makes this different from every other engineering challenge in human history. These constraints are coupled. They are not independent variables you can optimize separately. They interact. They push against each other. Solving one typically worsens another, often dramatically. Let me walk you through the coupling, because this is where the trap closes. Going faster reduces transit time. That is good. It means less biological degradation, less ecosystem strain, fewer generations born and dying on board. But going faster increases energy cost exponentially, because kinetic energy scales with the square of velocity. Going faster also increases the severity of interstellar medium bombardment, because each particle impact delivers energy proportional to velocity squared. So you need more shielding. But more shielding means more mass. And more mass means more fuel, and more fuel means more mass to carry the fuel, and the rocket equation spirals upward until the required fuel mass exceeds any reasonable engineering limit. You solved the time problem and broke the energy problem and the shielding problem simultaneously, so you try the opposite. Go slower. Reduce the speed to something like 1 or 2% the speed of light. The energy requirements drop. The shielding requirements drop. The interstellar medium becomes manageable, but now the transit time to Proxima Centauri stretches to 200 or 400 years. That means a generation ship. That means you need a self-sustaining closed ecosystem for centuries. An ecosystem that, as we discussed, no one has ever built. That means you need a stable society, a functioning governance structure, and cultural continuity across 10 to 20 generations of people who are born on the ship, live their entire lives on the ship, and die on the ship without ever seeing the destination. The history of every isolated human community suggests this will fail. Languages will drift, social structures will fracture, the mission purpose will erode into mythology. You solved the energy problem and broke the biology problem and the sociology problem. What about sending robots instead of people? That eliminates the biological constraints. No life support, no ecosystem, no generational drift. But it does not eliminate the energy cost, the shielding mass, the rocket equation, or the communication delay. A robotic probe still needs to be accelerated and decelerated. It still gets hammered by the interstellar medium. It still takes decades to arrive and years to send data back. And when it arrives at a system that no human will ever visit, carrying data that will be received by a civilization decades older than the one that launched it. The probe solves the biology problem, but the physics problems remain intact, and the meaning problem, what's the point of exploring a place no one can ever go, remains unanswered. What about laser-propelled light sails like Breakthrough Starshot? You solve the fuel problem by not carrying fuel. The energy comes from a ground-based laser array, and the sail carries no propellant. Brilliant. But now you cannot decelerate. A light sail pushed to 20% the speed of light by a laser near Earth has no way to slow down at the destination. It flies through the target star system in a matter of hours, takes a few photographs and continues into the void forever. And even during those few hours, it is being eroded by dust impacts at 60,000 kilometers per second, with no shielding because shielding would add mass that the laser cannot push. You solved propulsion and broke deceleration and survivability. Do you see the pattern? Every solution opens a new problem. Every optimization in one dimension creates a penalty in another. The constraints are not sitting side by side, waiting to be knocked down one at a time like bottles on a shelf. They're woven together, structurally linked, so that pulling on one thread tightens another. This is not an engineering challenge in the traditional sense, where you identify bottlenecks and address them sequentially. This is a system of coupled constraints with no feasible solution region, a space where, no matter which direction you move, you collide with a wall you are trying to avoid. This is the key insight that separates this argument from simple pessimism. The claim is not that any one of these problems is unsolvable. Some of them may well be solvable in isolation. We might someday build a fusion reactor compact enough for a spacecraft. We might someday learn to manage closed ecosystems over longer time frames. We might someday develop materials that can withstand relativistic dust bombardment. Any one of these breakthroughs would be extraordinary, and none of them would be sufficient, because the problem is not the individual walls. The problem is the architecture. The walls form a coupled system, a multi-layered constraint architecture, where the solution space for all constraints considered simultaneously may be empty, not small, not difficult to find, empty, non-existent, a mathematical void where no configuration of speed, mass, fuel, shielding, biology, and time satisfies all requirements at once. It is not difficulty. It is incompatibility. The requirements of interstellar travel conflict with each other in ways that cannot be resolved by optimizing any single variable, or even several variables simultaneously. Think of it like trying to build a vehicle that must function simultaneously as a submarine, an airplane, a reinforced bunker, and a working farm, and it has to operate in all four modes continuously for a century without any external resupply, maintenance, or rescue. Each of those capabilities is theoretically achievable on its own. Submarines exist, airplanes exist, bunkers exist, farms exist, but a single machine that does all four at once for 100 years with no support, that is not an engineering problem waiting for a breakthrough. That is a category error, a demand that exceeds what the individual components can deliver when forced to coexist under shared constraints. And the margins are not generous. Space is not a forgiving environment. One system failure on an interstellar ship, one, is not an inconvenience you work around. It is a death sentence, executed slowly, with no rescue possible, no replacement parts available, and no margin for retry. This is what I mean by the closed system civilization trap. It is not a dramatic phrase meant to inspire dread. It is a structural description. A civilization arises on a planet. It develops technology. It reaches the boundaries of its home system. It surveys the distances to other stars and calculates the energy costs. It models the transit times and the biological constraints. It runs the numbers on shielding mass and fuel ratios and ecosystem stability and generational sociology. And it discovers, not through failure, not through catastrophe, but through clear-eyed mathematical understanding, that the barriers are not sequential. They are simultaneous. You cannot solve them one at a time. You must solve them all at once. And solving them all at once may exceed the capacity of any civilization that operates within the laws of physics as we currently understand them. Maybe some future discovery changes this. Maybe there is a loophole in the physics we have not found yet. Some way to move mass across interstellar distances without invoking the rocket equation, without fighting the interstellar medium, without subjecting biology to decades of confinement, without breaking the temporal link between origin and destination. Maybe. But that loophole would not be an improvement on existing technology. It would be a violation of existing physics, and hoping for a violation of physics is not a strategy. It is a prayer dressed up in the language of optimism. The stack of constraints does not care about optimism. It does not care about ambition, or funding, or willpower, or time. It is a mathematical structure, and it says what it says, and what it says is that every door out of this system opens into another wall. And behind that wall is another door, and behind that door is another wall, and at no point in any direction does the path clear. Part 18. What is buried here with us? So let me bring this all the way home. The solar system is not a starting point. It is not a launching pad, not a nursery, not the first chapter of a longer story. It may be the whole story. The Sun, with its 8 planets, its dwarf planets, its comets and asteroids and moons, occupies a gravitational volume roughly 2 light-years in radius. Inside that volume, there's enough energy to sustain a civilization for billions of years. The Sun will continue fusing hydrogen for another 5 billion years. Earth, with management, could remain habitable for a significant fraction of that time. The resources of the asteroid belt, the moons of Jupiter and Saturn, the ices of the Kuiper belt, all of these are in principle accessible with technology not radically different from what exists today. The solar system is not small. By human standards, it is inexhaustibly large. There are entire worlds here we have never visited, resources we have never tapped, environments we have never studied. The idea that we need to leave is not based on scarcity. It is based on ambition, a specific kind of ambition that assumes the stars are the natural next step after the planets. But what if they are not? What if the planets are the last step? This is not a question about pessimism or optimism. It is a question about structure. The universe has rules. Those rules permit life. They permit intelligence. They permit technology. They permit awareness of a cosmos so enormous and so full of structure that the temptation to reach for it is almost irresistible. But the same rules that permit awareness also restrict motion. They impose speed limits, energy costs, mass penalties, and time constraints that scale against interstellar travel with a consistency that feels less like coincidence and more like architecture. The Fermi paradox, viewed through this lens, is not a paradox at all. If every civilization that arises is confined to its home system by the same set of overlapping physical constraints, then the galaxy would be exactly what we observe, full of stars, potentially full of life, and perfectly silent. No radio signals, because no one has built interstellar transmitters of sufficient power to be detected. No megastructures, because the energy demands of interstellar travel consume any surplus before it can be directed outward. No visiting probes, because no probe has ever been built that can survive the journey. The silence is not evidence of absence, it is evidence of walls. There is a philosophical dimension to this that deserves acknowledgement, even if it cannot be resolved. Are we early, one of the first civilizations to arise, with the great expansion of life through the galaxy still ahead of us? Are we average, one of many civilizations that have arisen and remained confined, each one thinking it is the first, each one discovering the same walls? Or are we trapped, not by accident, but by the fundamental design parameters of a universe that produces observers, but not travellers, consciousness, but not mobility? The simulation hypothesis enters here briefly as speculation rather than science. Some theorists have proposed that if the universe were a computed reality, the constraints on interstellar travel would be analogous to computational boundaries, limits imposed not by physics, but by the architecture of the system running the simulation. This is interesting as a thought experiment, but irrelevant as an explanation, because it is not testable, not falsifiable, and not necessary. The constraints we have described are fully explained by known physics. You do not need a simulation to produce a cage, gravity and thermodynamics are sufficient. What remains, after all the numbers and all the equations and all the failed experiments and all the cosmological projections, is a feeling. A feeling that the universe is showing us something, showing us everything, and keeping it just out of reach. The stars are there, the galaxies are there, the exoplanets with their water vapour and methane and carbon dioxide are there. We can see them, measure them, name them, dream about them. We can build golden records and strap them to our fastest machines and fling them outward into a darkness that will swallow them whole. But we cannot follow. The solar system is not a prison. That word implies malice, and there is none. The universe is not cruel. It is indifferent. It permits life, and it imposes constraints on motion, and the constraints happen to be strong enough that the life remains where it arose. The sun is not a jailer. It is a host, and the system it anchors, this small, warm, gravitationally bound collection of rock and ice and gas, is not a way station. It is the destination. What is buried here with us? Everything we will ever build, everything we will ever think, every poem, every equation, every child, every city, every song, every attempt to leave, every failure, every generation that looks up at the same stars and feels the same pull and runs the same calculations and arrives at the same answer. All of it, here, orbiting a single ordinary star, in one arm of one galaxy, in a universe that stretches out in every direction for billions of light years and does not care whether we cross it or not. If that is the truth, and the evidence, stacked layer upon layer, suggests that it may be, then the question is not how to escape. The question is what to do with the time we have, in the place we are, knowing that the light from distant galaxies is the closest we will ever get to them. And whether that knowledge makes this place smaller, or whether in some strange and human way it makes it enough.